When I switched from experimental radio astronomy to working on policy issues, the first paper I ever wrote was on the negative externalities of coal, and I continued to write a number of other papers on that subject. When I realized that I was going to be speaking here today, I asked my colleague Nick Mueller and his doctoral student Brian Sergey to run one of their models to get an estimate of the number of excess deaths a year from coal plants in the U.S., or from coal combustion generally in the U.S., and they get numbers that range between 7,000 and 15,000 deaths a year, which, as you heard, is down by roughly a factor of 2 from the numbers in 2010, and that's because of two things. We are dramatically cleaning up emissions of sulfur dioxide, and we're also making less electricity from coal. The situation, as Steve just told you, is much more dire elsewhere around the world, and I won't repeat the numbers, but they have a long way to go. But without minimizing the local and regional impacts of coal, today I see the bigger problem as the need to very rapidly decarbonize the energy system. This is a plot, for example, from a recent piece that Glenn Peters and colleagues did. I won't go through the details, but basically the answer is that if we don't get down to almost zero or maybe even negative emissions in the next 2 or 3 decades, we're not going to make the 2-degree target that was agreed in Paris. And doing that, in my view, is going to take a portfolio of essentially everything we've got. Indeed, to meet the 2-degree target, we're almost certainly going to have negative emissions. Now, probably most of the people in this room know that when I put a pulse of CO2 into the atmosphere, it decays, but that a century or two out, there's still 30 or 40% of it still in the atmosphere. But while Americans now know that CO2 comes from burning fossil fuel, and they also know that CO2 causes climate change, Americans think that atmospheric residence times for carbon dioxide is the same as that of conventional air pollution, and hence they can plausibly think, well, you know, if this climate stuff is ever real and gets serious, we'll just fix it by stopping emissions when things get serious. Why am I able to say that? Well, with one of my doctoral students, Rachel Dryden, and a couple of excellent behavioral social scientists, and Bostrom and Wendy Brundebrun, we did a study looking at people's judgments about residence time for conventional air pollutants, the black bars on the left, and carbon dioxide, the light bars on the right. I won't go into the details of how we did the study. We obviously didn't ask for residence time, but you can see that people think that the CO2 residence time is roughly the same as air pollution and about a decade or two. I want to talk a little bit then about decarbonizing the system, and since this session is mainly about electricity, I'll focus on the electricity sector. As you've heard a couple of times now, that mix has changed fairly substantially over the years. In 1950, coal was by far the dominant source for electric power generation. By the 70s, gas had begun to come in. And the two main reasons for these changes have been, first, the dramatic reduction in costs, because solar has dropped so dramatically, it dominates this plot, but wind and gas, of course, also. And then environmental and other regulations, things that entail cleaning up the conventional pollutants and subsidizing wind and solar. So today, if it's blowing, wind is probably even cheaper on a per kilowatt hour basis than natural gas. But you got to remember that both wind and solar are intermittent, and as Jay Apt will tell you in a few minutes, you have to worry about how you fill when the wind stops blowing or the sun stops shining. So this is a curve that Nick Brown, the CEO of the Southwest Power Pool, shared with us recently. During March, they exceeded 60% wind for a period, but then there are these two gaps you see where the wind stopped blowing, and so gas and coal had to ramp up to fill in. This is, of course, a an underlying problem when people start talking about 100% renewables. 100% carbon-free I can understand. 100% renewables I have some difficulties with. Now, Steve Pacala and Rob Soklow years ago argued that the way to decarbonize the energy system is with a series of wedges. You have a wedge of energy efficiency, a wedge of carbon capture and sequestration, of renewables, nuclear, and so on. So in my last few minutes, I'd like to go through and talk a little bit about where we stand with respect to achieving those wedges. For both coal and natural gas, we're going to have to, if we're going to continue to use them, and they are, as you can see here, right now, a major supplier of energy for the electricity system, we're going to need carbon capture and deep geologic sequestration. Those technologies exist, but as long as there's really no cost associated with emitting carbon dioxide to the atmosphere, we're not going to get over the hump in terms of the learning curve. And learning curves are really important. Here, for example, are learning curves that Ed Rubin, my colleague, has put together. The top one for sulfur controls, the bottom one for nitrogen controls. And you can see the first few plants we built didn't work very well. And then, you know, finally we got a design that worked and we started down the learning curve. We need to get to that point for CCS. We also, of course, need to work on things like the legal and regulatory arrangements for deep geologic sequestration. Now, there have been some recent initiatives to provide tax incentives to do capture. The motivation here is principally to capture CO2 for secondary oil recovery, so it's going to be net positive in terms of CO2, but it may help to at least jumpstart the development of the technology. Jay App's going to talk a bit about wind and solar, so I won't. But the other renewable source, actually the largest renewable source at the moment for the U.S. power system, is hydro. And we can get more from places like northern Quebec, but the resource is very limited. And there are a lot of other demands on water for fish, for agricultural irrigation, for Native Americans, and so on. Until recently, for the last 2 or 3 decades, nuclear has been about 20% of all U.S. electricity. But analyses my colleagues and I have done suggest that there will not be a new nuclear wedge for at least the next several decades. Now, maybe Ashley can increase our optimism a bit, but we're not going to build any new 1,000-megawatt nuke plants in the country. The 2 that are still under construction have had enormous cost overruns. We've abandoned a couple of such plants, and we're also shutting down plants because, for a variety of reasons, one of which is the low cost of natural gas. Work we've done recently looking at the research programs at the DOE Office of Nuclear Energy suggests to us that we're essentially dead in the water, that it'll be at least 2050 before any advanced reactors become commercially viable in this country, unless, as Ashley may argue, there's a dramatic change. And that just leaves factory manufactured small modular reactors. And we've been trying really hard to construct a scenario that identifies a large enough market of SMRs domestically to make this take off. So we've looked, for example, of plants that desalinate water when the wind is blowing and make electricity when the wind stops blowing. We've looked at thermal loads met with SMRs rather than coal. We've looked at things like using them for DoD bases. And we conclude that no nuclear wedge is going to develop on the time scale of the next few decades. So the bottom line is that to achieve the necessary massive transformation of the energy system, we're going to need a portfolio of everything we've got. I've already told you that we've taken the nuclear wedge off the table. There aren't any silver bullets. We really need to get cracking in terms of developing some of these wedges. We shouldn't wait too long because, after all, we've only got one planet.